Hello, everyone. This section is 5.5, and it's the last section in this chapter. Of course, and it closes Calc 1. This substitution rule, let's give an example here for this integral. This indefinite integral, when you look at the table, you're not going to see an antiderivative for it. For substitution rule, we'll take care of it. So we'll explain in a minute what this substitution rule is. Because remember, there are some derivatives that come from, for example, from the chain rule. So those that they are not simple just to be in the table. So what if we're supposed to have 1 plus x squared as a u, just like it's done in pre-calculus for u substitution, let's say that, then we can differentiate. And here we have to understand the idea of differentials. So let's say you have x squared, and you say derivative of x squared. That means you're doing the x squared dx, right? Then which is 2x. So similarly here, so this dx is that differential. So if we have a u, as we did in implicit differentiation, if we do du to dx, so that's going to be d to dx, and that's going to give us 2x, right? So du to dx is equal to 2x. So if you multiply both sides by dx, right, you're going to get a du equal to 2x dx. So now those differentials are allowed here. And so if you have this, then these differential du equal to 2x dx, so now you see where it came from. Then we can consider this integral, which is this one here, to substitute this with the u. And you see this 2x dx is going to be replaced by the u. And that's going to give us this kind of simplified form. So we can replace this square root of 1 plus x squared times 2x dx with the square root of u du. If we do that, then this is easy to do as far as the antiderivative, right? Because this is u to 1/2, and we can add 1 and divide by that number, and which is 3/2, and that's going to give us by reciprocal 2/3 plus c. But remember that the integral started with 1 plus x squared, and once you use this kind of u substitution, you need to revert it back to bring it back to the x format. So you replace back. So in pre-calc, when the u substitution is used, step 1 you use substitution, step 2 you use the back substitution. So I still didn't work yet this substitution. I just tried to give an example to it. So the check is, if you differentiate what you come up with, you should find what's inside the integral, right? Yeah, so if you differentiate this antiderivative, you should get this inside. So this form that we're looking at here is f, some function with g of x inside, and times the derivative of g of x. So if we have this type of form, we can use this u substitution. And just to remind you that if you have this composition, that's the one we did. The derivative 4 is f prime, which is this first, with g of x stays inside, times the g of prime. So outside to inside. That's what we did for using the chain rule. And here's just explanation to it and how to prove that it works. So let's look at what is this substitution rule. The substitution rule says if you have, so if you have a u equal g of x is differentiable function whose range is an interval I and f is continuous. So f is continuous and g prime is differentiable. If these two conditions are met and you see the integral and you can tell that there is a g of x inside f, a composition of a function, multiply with that g prime of x, then you can, and of course you see this, that's an indefinite interval, then you can integrate with using the u as g of x. So u as a g of x. You can do this substitution and move on with it. But watch for this substitution rule. This is an indefinite integral, right? And of course, you see the differential, like the differentials, du and dx. So this rule says it is permissible to operate with dx and du after integral signs as if they were differentials. So let's look into an example. Looking at this one, we can see that maybe we can rewrite it this way. X cubed dx. So you see this function here, it's inside. This can be a g of x. And this can be the f, right? And in that case, and this can be the g prime of x. So this inside, if you take this inside and call it a u, then the differential is going to be, of course, you're going to do du to dx is going to be 4x cubed, the derivative dx. So if you multiply by dx both sides, I did it before that, this is the derivative. So if you multiply by both sides, you get that. So we have a 4 that is that is not existing here. So we can put a 4. Why not? We have a 4 that is missing here. So we can put a 4 there. But of course, when you do a 4 there, you change the value of this integral, or you change the output. It won't be correct. So you need to cancel the 4 by multiplying by 1/4, right? So now we can see that I have the du there, and I have the u. So this is a u and this is a du. So now the integral, we have a cosine of u times a du, right? So let's rewrite this even to match. To switch him. And complete this one. So we have x cubed dx, right? That's what we have here. And if you solve for x cubed dx here, you will have 1/4 du. So that's why this 1/4 du is there, because that replaces the x cubed dx. So if we put u instead this, it becomes cosine of u, and we need x cubed dx. X cubed dx is gonna be 1/4 du. So now 1/4 can come outside in the next step, and now we have an integral that just comes from the table, and that's 1/4 sine of u plus c. Remember the start was with the x, so we back substitute to find with the x value. All right, okay. So the difficulty of this is to recognize that we have a form in which this substitution can be done, and the homework is a little bit even easier because the u is given. But let's look at the definite integral part of it. There is, of course, here, of course, it's possible to do it this way, but this is the one I like when it comes to definite integral, because this example is much bigger than what it is when you work in different systems, and you'll see in math or in engineering or some other applications. If you are in this system, let's call it system 1, and somehow things are not working and you transition to system 2, then you need to work within system 2. Everything now is going to be defined based on system 2, right? And that should get somewhere. So this is the idea I like. So we'll use this one because we need to have the understanding that once you transition into a system, everything has to transition there. So here, if you have A to B, which means that we have now a definite integral and you have the same form that can use a substitution, look at the upper and lower limits. They also convert into that, and I'll show it into example. So here you have, let's say this is system uses x, and this is system uses u. Here x equal a, x equal b. Here you're not going to have a and b because that's x. So now we need to find what does this mean in terms of u, and what does this mean in terms of u? Because this system does not use the x, it uses u, right? So here is an example. We have just this square root of 2x plus 1 dx and 0 to 4. And of course, we can use that number 6 if we go back to it. Here, right there. If we use this, right, then we will need to change the upper and lower. So let's do this first. If you do the u as 2x plus 1, right, then this du dx is going to be a 2. So what du is 2 dx, right? And the problem here is we don't have a 2, we just have a dx. So we need a 2 dx. So before we do this, let's show it. If we have 0 to 4, 2x plus 1, now that we're thinking about it, we need this. So you need to cancel that by doing the half, right? So let's write all of them next to each other. Half a 2 a dx. Just like they cancel each other and you just have a dx. So if u is 2x plus 1, then a du is going to be 2dx, right? Which means since we only have a dx there, we don't have a 2, we're going to need to use the half. So dx is going to be a half du. So when you do this, you're going to need to do a half du, or this way. So I didn't work yet about the definite integral, but just to figure out if it were the indefinite integral, this is what we'll do, and of course we'll add the c there. But now if it's this definite integral, you see if I use 0 and 4 here, that's not going to be correct because this is x and this is x, and now the system is using a u. So this needs to be transitioned. We need some u here as a lower limit and some u here as the upper limit. So we will go back to this and say if x is 0, then u is 1, right? And if x is 4, then u is 9. And let's show the steps here. So maybe I'll show here before I do that. So this is 9, not a 4. So 1, 9, square root of u du. And that's going to be 1 to 9, u to 1/2 du, right? And now that's a good picture. And which is this? See. And we can go ahead, figure out what is the antiderivative to this. Well, the antiderivative to 1/2 is you're going to add 1 and you will divide by it. And that's going to be u to 3/2 over 3/2. So it's going to be 2/3 times u to 3/2. And you have the 1/2 sitting there. And this 2/3 with 1/2 is going to give us 1/3 outside. Then now we have the lower limit is 1, the upper limit is 9, and we use that and we get the answer. So as you notice from this, why it's good to use this method for definite integral, because you don't have to go back to x. It actually calculates it and it finishes it there. So there is no need to go back to x when you use this. So you transition from this x to u, and if you do the g of a and g of b, this calculates it and it's done. There are two nice properties I think we spoke about, but now just to look at them in more details. When we did looking at integrals as far as geometry, we talked about the graphs. So if a function is even, and these are helpful and they simplify some work, and I'll show you a nice example. So if f is even, that means if you have a point here, then you have a point here on a graph, right? Then let's say this would be, let's say, an even function, right? and let's say we're taking from negative a to a, you see in this case, these areas are the same and they're both positive. So there is no need to calculate from negative a to a. You can just take 2. So if this is here a1 and this is a2, a1 is same as a2. So a1 area plus a2 area is just going to be 2 of one of them, right? And or 2 of a2. That's it. So it simplifies. So it helps to see if this is even, then the calculation simplifies. Even better if we recognize that it is odd. If it is odd, then it's symmetrical to origin, right? So we did a few examples. Then from negative a to a, if this area is, let's say, a3, and this one is a4, a3 and a4 are same as far as absolute value, but they're opposite. A3 is negative and a4 is positive. So if you add a3 with a4, you're going to get 0. So that's the property there, and that helps simplify. And why this one is good, let's just do an example. Let's say from negative 4 to 4 for this polynomial. By knowing for the odd and even, and by knowing the other properties, as we can split these for the sum and difference, look, we can do this. You know, if you put these terms with odd exponents together, this is going to be an odd function. And what's left here is the 6x squared minus 3, and the only exponent here is even, so that's going to be an even function. If this is an odd function from negative 4 to 4, it's, of course, it's crossing the 0 line, right? Then for odd, that's going to be just 0. We don't need to calculate that. So that's the power of this knowledge here. For this other one as well, negative 4 to 4, it crosses, so we have double. We have, so instead doing 2, from negative 4 to 4 and calculate for negative 4 and 4, 0 actually is easier to calculate. So we can do this, and of course 0 plus that is just going to be the antiderivative, and this for 4, and this for 0, which means 0, right? And that's going to give to 32. So by knowing these properties, the work is simplified. And here a little more pictures and illustration for it, for the even and the odd, and how the areas here are alike, and so that's a double, and here they're opposites, so they cancel. And these are 2 examples. So for example, this one, x to the 6 plus 1, that's an even function. So from negative 2 to 2, we can take a 2 double and calculate. And this 10 tangent x over 1 plus x squared plus x to the 4th, you can test it. You find that it's an odd function. So imagine working on this, right? From negative 1 to 1, it's going to be complicated. but by finding out that this is an odd function, the answer is automatically 0. So we can maybe try some other examples from the homework. You have 5.5, let's say number 4, and you're given sine squared theta, cosine theta d theta, and this is u sine theta. This is given. So if this is given, then du is going to be cosine theta d theta, right? So this is going to be du, and this is going to be u square. And this is easy to find the antiderivative. It's just going to be u cubed over 3 plus c. And so now we need to go back to theta. So we're going to say it's sine theta cubed over 3 plus c. Let's do number 5. Same, this is given. So if this is given this way, then du dx, and look here, you have x to the 4th dx, which is this part. So we need to do this to get that part, which means when you put the u here, right, then this is going to be 1/5 du, 1/5 du, or 1/5. And the antiderivative for this one is just going to be ln u, which we need to take back to x by doing ln x to the 5th minus 6 plus 6 plus minus 6 in the absolute value plus c. All right, I think we can discuss some more examples in class, but this does the work in understanding what this substitution works, and you can make maybe own examples and practice, and this is one of the techniques. Thank you.